Hello, this is Professor Kuehn. We've been looking at Chapter 9 in A Student's Guide to the Great Physics Text, Volume 3. In this chapter is contained a lecture by Hermann Helmholtz. It's called On the Conservation of Force. We got up to about page 107 or 108 in my last lecture, so let's pick up where we left off. At this point, Helmholtz was talking about the use of pulleys, and the principle by which pulleys work is the same principle by which many other machines work. And it is this, that whatever work you put into the system is going to be equal to the work that you get out of the system. So, for example, in figure 9.2, if one were to grab with their hand a rope on the end of this sophisticated pulley arrangement, if one were to apply a force at point A and move the hand by a distance dA, that would be a way of computing the work that you're doing on this system. And according to the law of conservation of force, as he puts it, the work that you're doing with your hand is exactly equal to the work that is done in lifting this mass. But by the clever arrangement of these ropes, one can make it so that the distance the mass is lifted is going to be less than the distance that the hand moves. So in this particular example, the distance that the mass moves is going to be up by 1/4 of the distance dA that the hand moves. And as a result, in order to keep these two sides of the equation equal, you get 4 times the force of A. This is the force that can be applied to lift the mass. So in other words, one can lift a mass, one can lift a weight 4 times heavier than the force that the hand is applying, although it lifts through a smaller distance than the hand had moved. So that's where we left off last time. So let's talk a bit more about how to apply this principle that the work one puts into a machine like this is equal to the work one gets out. Another example is a lever, and this is described on the next page, on page 109. There's a figure 9.3 depicts a lever. And so you might see here that in this lever, on the right-hand side of the lever is a very small weight, and on the left-hand side is a large weight. And in falling the distance from B to B prime on the right-hand side, from here down to here, the left-hand side, large weight, can lift from A to A prime. And the ratio of these is such that the force on the right-hand side times the distance on the right-hand side is equal to the force on the left-hand side times the distance on the left-hand side. And once again, that is consistent with this principle that the work that is put in, you might think about that as the work that is done by the weight on the right-hand side, is exactly equal to the work you get out. That is the work that it takes to lift the mass on the other side. Of course, as Helmholtz mentions, this assumes that there's little or no friction in the joint or the fulcrum about which this is rotating. Okay, and then he goes on to talk about a number of other machines, such as the crab winch. And in that case, one can apply a small force in rotating this handle on the left-hand side of figure 9.4, and by moving the hand for a very large distance as the hand rotates this winch around, you can lift a very heavy weight that's attached to the rope wrapped around the drum. Although the hand might apply, let's say, 50 pounds and move over a large angle, you could lift a much heavier weight, let's say 200 pounds, but it would be lifted a much smaller distance. And once again, that obeys the rule that the work you put in with your hand is equal to the work that you get out. That is the work that it takes to lift the heavy mass by a certain distance. Okay, so we have sufficiently talked about the concept of work and quantity of work. So what I want to do now is I want to move on to chapter 10, where we talk about kinetic and potential energy. This is, again, not the terminology that Helmholtz uses. The term energy was established a little bit later with the work of, I believe it was Thomas Young. I'll have to come back to that, though. The work of Thomas Young used the term energy. But in this chapter, we talk about specifically kinetic energy at the outset. So in the last chapter, we described how an overshot wheel works. That is, when a portion of water falls due to the action of gravity from one height down to another, it can expend a quantity of work equal to its weight times the distance through which it falls. But in some cases, as Helmholtz mentions at the beginning of this chapter, in some cases there's not sufficient drop in the altitude of a river, like if there's not a waterfall, rather just a quickly moving river. In some cases there's not a sufficient drop in the river so as to make use of the force of gravity in this way. Nonetheless, we can still get work. Work can be accomplished by a flowing river. How is this done? That's what he's describing with the undershot wheel. One can use the velocity or speed of the water to accomplish work as well. So just as the work can be accomplished by allowing water to move under the action of gravity from a high altitude down to a low altitude, so too work can be accomplished by allowing water to exert a force on an obstruction, in this case a wheel, and in so doing the water decelerates from a high speed down to a low speed. So if we were to depict this, we might imagine this river flowing in this direction. And if you have this wheel dipped into it, as is depicted in this diagram, with these paddles attached to it, as the river flows past, this wheel can be made to rotate, and you might imagine if we have a drum on this and a rope attached to it, we might be able, for example, to hook this up to a pulley, and if we have another pulley like this, we could lift a weight, for example. We could do work using the speed of this flowing river. However, what happens is that if the river is flowing with some high speed at this point, when it strikes the paddles here, it's going to slow the river down. It's going to lose some of its speed. So there's a relationship between the loss of speed of the river and how much work that can be done in lifting up this mass or doing whatever other kind of work we want to. There's another example that of the use of moving objects to accomplish work, and in so doing slowing them down, that Helmholtz gives on the subsequent page. This is on page 115. This is an example of what's called the ballistic pendulum. So the idea is this: if one were to have a pendulum, so a string hanging from a ceiling, and one were to put a block, a penetrable block, right here, and that block has some mass m, and if one were to fire a bullet at this block, so let me imagine we fire a bullet at this block. This bullet has some initial speed, v initial, and when it strikes this block, it embeds itself in the block, and the block then swings upward, and it gets to some maximum height. And the height to which it gets depends on the speed with which the bullet struck it. So the altitude gain, or the height gained by this block, depends on the speed of the bullet. In other words, there's a relationship between the work that can be done in lifting this block and the speed of the bullet. Of course, the bullet comes to rest after it's been embedded in the block and the block has swung up through this particular angle and come to a rest. Now, one can study the relationship between the speed of the bullet and how high this block can be lifted. So the question is, how much work? How much work can be accomplished? This is the general question that we're asking. How much work can be accomplished in bringing a moving mass to rest? So kind of how much work is inside of this moving block, if you want to, or moving bullet, if you want to think about it that way? Well, one can do experiments, one can plot the height that the block swings to as a function of the velocity initial of the bullet, and if you were to do this, one would find that the height increases with the velocity. And in particular, one can find that the height is proportional to the square of the velocity. It's not just linearly proportional to, but it goes as the square of the velocity. And if you were to also try to measure the height that the block swings to with respect to the mass of the bullet, keeping the velocity the same, one would find that the height that it swings to is also proportional to the mass of the bullet. So one can do these sort of empirical experiments and seeing how the height of the block, the final height of the block, depends on the speed of the bullet and the mass of the bullet. And eventually, this leads to this idea that the work that can be done by the bullet, the work that can be accomplished by a speeding bullet is given by the work it can do is equal to 1/2 its mass times its velocity squared. That's the amount of work that can be done by this bullet. Okay, now I haven't derived this for you except to motivate it by saying the work that can be done goes as the velocity squared and the work that can be done goes as the mass of the bullet. It might not be obvious at all to you where this factor of 1/2 comes from. So I'm just sort of telling you what this formula is that relates the work that the bullet can do to its mass and its velocity. By the way, this quantity right here, 1/2 mv squared, is today called the kinetic energy of the bullet. The kinetic energy of the bullet. And it's interesting that this is called energy. So first of all, the word kinetic has to do with motion. So it's an energy associated with the motion of an object. And energy comes from two root words, en meaning inside, and erg is the Greek word for work. So the word energy literally in Greek means something like the work that is inside of the moving object, the work that's inside of this bullet, for example. And that captures this idea that a moving object can do work and it has contained within it in some way an ability to do work. It's energy. Okay, so tell you what, why don't we stop there and we'll talk more about this in the next lecture.